According to the National Electrical Code, you cannot install both number 4 and number 8 copper conductors in 3/4-inch EMT or PVC. The maximum number of number 4 AWG copper conductors that can be installed in 3/4-inch EMT or PVC is 2. The NEC does not permit the installation of number 8 AWG copper conductors in 3/4-inch EMT or PVC. For a furnace installation, you can use the following wiring configuration: 2 number 4 AWG copper conductors for hot and neutral and 1 number 10 AWG copper conductor for ground. This wiring configuration requires a minimum conduit size of 1-inch EMT or PVC. Always refer to the latest edition of the NEC for accurate and up-to-date code requirements. To elaborate further, let's delve into the specifics of conduit fill calculations and NEC tables to understand why these limitations exist. Conduit fill refers to the percentage of the cross-sectional area inside a conduit that is occupied by conductors. The NEC sets limits on this percentage to ensure adequate space for heat dissipation, ease of pulling conductors, and prevention of damage to the conductor insulation. The allowable fill percentage varies depending on the number of conductors within the conduit. For example, when there are 2 or more conductors, the maximum allowable fill is typically 40%. To determine the appropriate conduit size for a given set of conductors, you'll need to consult NEC Chapter 9, Table 1, which provides the dimensions and cross-sectional areas of different types of conductors in conduit. First, determine the total cross-sectional area of all conductors to be installed. For number 4 AWG copper conductors, refer to NEC Chapter 9, Table 5, which lists the dimensions of insulated conductors. Find the cross-sectional area for the specific type of insulation used in the number 4 conductors, such as THHN or THWN. Similarly, find the cross-sectional area for the number 8 AWG copper conductors and the number 10 AWG copper conductor. Add the cross-sectional areas of all conductors together to obtain the total conductor area. Next, consult NEC Chapter 9, Table 4, which lists the dimensions and cross-sectional areas of different conduit types, such as EMT and PVC. Determine the inside area of the 3/4-inch EMT or PVC conduit. Calculate the allowable fill area by multiplying the conduit's inside area by the maximum allowable fill percentage, typically 40% for more than 2 conductors. Compare the total conductor area to the allowable fill area. If the total conductor area exceeds the allowable fill area, you must increase the conduit size. In this case, the combined cross-sectional area of 2 number 4 AWG copper conductors and 3 number 8 AWG copper conductors exceeds the 40% fill limit for 3/4-inch conduit, requiring a larger conduit size. The NEC specifies that for a furnace installation using 2 number 4 AWG copper conductors for hot and neutral, and 1 number 10 AWG copper conductor for ground, a minimum conduit size of 1-inch EMT or PVC is required. This is because the combined cross-sectional area of these conductors fits within the 40% fill limit for a 1-inch conduit. It's crucial to remember that these calculations are based on specific conductor types and insulation. Different insulation types have varying thicknesses, which affects the overall conductor diameter and cross-sectional area. Always refer to the NEC tables for the correct dimensions and areas for the specific conductors you are using. Furthermore, the NEC may have local amendments or interpretations that could affect conduit fill requirements. It's always best to consult with a qualified electrical inspector or engineer to ensure compliance with all applicable codes and regulations in your area. In addition to conduit fill, other factors to consider when selecting conduit size include rating of conductor ampacity due to the number of conductors in a raceway, physical protection of conductors, and ease of installation. Rating refers to reducing the allowable ampacity of conductors based on the number of current carrying conductors in a raceway or cable. The NEC provides rating factors in Table 310.15 colon. If the number of current carrying conductors exceeds 3, the ampacity of each conductor must be rated according to the table. This is to prevent overheating of the conductors due to mutual heating effect. Physical protection of conductors is another important consideration. Conduit provides mechanical protection to conductors, preventing damage from impact, abrasion, and other environmental factors. The type of conduit used should be appropriate for the specific application and environment. For example, PVC conduit is often used in underground applications due to its resistance to corrosion, while EMT is commonly used in indoor applications. Ease of installation is also a factor to consider when selecting conduit size. Using a larger conduit size than required can make it easier to pull conductors through the conduit, especially when dealing with long runs or multiple bends. This can save time and effort during installation. In summary, determining the appropriate conduit size for a given set of conductors requires careful consideration of conduit fill limitations, conductor ampacity derating, physical protection requirements, and ease of installation. Always refer to the latest edition of the NEC and consult with a qualified electrical professional to ensure compliance with all applicable codes and regulations. Remember, the NEC is updated regularly, typically every 3 years, to reflect changes in technology and best practices. Staying up to date with the latest edition of the NEC is essential for ensuring safe and compliant electrical installations. Now let's talk more about conductor types and their specific applications. The choice of conductor type depends on several factors, including the application, operating temperature, and environmental conditions. Some common conductor types include THHN, THWN, THW, and XHHW. THHN stands for thermoplastic high heat resistant nylon. It is a popular choice for general purpose wiring in dry locations and has a maximum operating temperature of 90 degrees Celsius. THWN stands for thermoplastic heat and water resistant nylon. It is suitable for use in both wet and dry locations and also has a maximum operating temperature of 90 degrees Celsius. THW stands for thermoplastic heat and water resistant. It is similar to THWN but does not have a nylon jacket. Its maximum operating temperature is typically 75 degrees Celsius. XHHW stands for cross-linked polyethylene high heat and water resistant. It has excellent resistance to moisture and heat and is often used in underground applications. Its maximum operating temperature is typically 90 degrees Celsius. When selecting a conductor type, it's important to consider the ambient temperature and the operating temperature of the equipment being powered. The conductor's ampacity must be derated if the ambient temperature exceeds 30 degrees Celsius or if the conductor is installed in a high-temperature environment. The NEC provides ampacity correction factors in Table 310.15b2 for different conductor insulation types and ambient temperatures. In addition to conductor type and ampacity, the method of installation also affects the allowable ampacity of conductors. The NEC recognizes several different wiring methods, including conduit, cable, and open wiring. Each wiring method has its own set of rules and requirements. For example, when conductors are installed in conduit, the ampacity must be derated if the number of current carrying conductors exceeds 3. When conductors are installed in cable, the ampacity may be limited by the cable's overall temperature rating. Open wiring is typically only permitted in industrial or agricultural settings where it is not subject to physical damage. Grounding is another critical aspect of electrical safety. A grounding conductor provides a low impedance path for fault current to return to the source, allowing the overcurrent protective device, such as a circuit breaker or fuse, to trip and clear the fault. The NEC requires all electrical equipment and systems to be properly grounded. The size of the grounding conductor is determined by the size of the ungrounded conductors. The NEC provides grounding conductor sizing tables in Article 250. The grounding conductor must be connected to a grounding electrode system, which typically consists of a ground rod, crown plate, or underground water pipe. The grounding electrode system provides a connection to the earth, which helps to stabilize the voltage and provide a reference point for the electrical system. Proper grounding is essential for preventing electrical shock hazards and protecting equipment from damage. In addition to grounding, bonding is also important. Bonding refers to connecting all metal parts of an electrical system together to create a continuous electrical path. This helps to equalize the voltage between different metal parts, reducing the risk of electrical shock. The NEC requires all metal enclosures, raceways, and equipment to be properly bonded. Bonding can be achieved using bonding jumpers, bonding screws, or other approved methods. Proper bonding is essential for ensuring electrical safety and preventing equipment damage. Overcurrent protection is another critical aspect of electrical safety. Overcurrent protective devices, such as circuit breakers and fuses, are designed to protect conductors and equipment from damage due to excessive current. The NEC requires all electrical circuits to be protected by overcurrent protective devices. The size of the overcurrent protective device must be matched to the ampacity of the conductors being protected. The NEC provides overcurrent protection requirements in Article 240. Circuit breakers are automatic devices that trip and interrupt the circuit when an overcurrent occurs. They can be reset and reused after the fault is cleared. Fuses are one-time devices that melt and interrupt the circuit when an overcurrent occurs. They must be replaced after they have blown. Both circuit breakers and fuses provide overcurrent protection, but they have different characteristics and applications. Arc fault circuit interrupters, or RFCs, are special types of circuit breakers that are designed to protect against arc faults. Arc faults are dangerous electrical conditions that can cause fires. RFCs are required in many residential circuits, such as bedroom circuits, to protect against arc faults. Ground fault circuit interrupters, or GFCIs, are special types of circuit breakers that are designed to protect against ground faults. Ground faults occur when current leaks from the circuit to ground. GFCIs are required in many locations where there is a risk of electric shock, such as bathrooms, kitchens, and outdoor areas. In summary, electrical safety is paramount. Proper grounding, bonding, and overcurrent protection are essential for preventing electrical shock hazards and protecting equipment from damage. Always follow the NEC and consult with a qualified electrical professional to ensure safe and compliant electrical installations. Remember to always de-energize circuits before working on them and use appropriate personal protective equipment such as insulated gloves and safety glasses. Electricity can be dangerous if not handled properly, so it's important to take all necessary precautions. Finally, it is extremely vital that for any electrical work undertaken, that you seek out a professional and licensed electrical contractor. Electrical work should not be taken lightly and extreme harm can occur if done incorrectly.